All right. Our speaker today is Nathan Dunfield. He's going to tell us something about Floer homology, orderable groups, and taut foliations of hyperbolic string manifolds. Experimental study.
Thank you, Ilya. It's always a pleasure to address this audience. The slides for this talk are already posted at this URL. I do that for two reasons. The first is that, one disadvantage of slide talks is the stuff tends to fly off the screen very fast, and if you weren't spaced out for a second, all of a sudden you'd have no idea what's going on. That's the real reason, but the other reason is so that this way, if I look out at the audience later in the talk and somebody's fiddling with their phone, I'll think, they're just looking to see what I said on slide 5. So, as my title suggests, I want to talk about three things which at first glance will not seem to have anything to do with one another. I'll talk about Floer homology of the kind that Tom Rofka was telling us about last week in his two talks. I'll talk about a property of groups, whether they have left invariant orders, and then I'll talk about certain kind of codimension 1, two-dimensional object in a hyperbolic 3 manifold, namely a taut foliation. Excuse me. Okay, so the kind of 3 manifolds I will be thinking about today will be rational homology 3 spheres. So these are closed oriented 3 manifolds whose rational cohomology or homology is the same as that of S3. So you should think of perhaps something like a lens space as a sort of basic example. I'll always insist my manifolds be irreducible, so not connect sums in particular of other 3 manifolds. And the conjecture around which this talk revolves is the following. So I'll just say it, but I realize that none of these 3 statements make any sense. And in fact, the first half hour of my talk will be devoted to attempting to indicate what they mean. So the conjecture says that if you have an irreducible rational homology sphere Y, the following 3 things are equivalent. The first, that its Floer homology, whatever that is non-minimal. So there's some interesting Floer homology. The second is that the fundamental group of Y has some additional structure called a left order. And then the final condition is that Y has a co-orientable taut foliation. So you should think of each of these statements as saying that Y is somehow complicated. There's some extra Floer homology you might not have. There's whatever it is this means, this sort of order on the group that obeys certain properties. And then you have this foliation codimension 1 object. It's kind of like an incompressible surface or a subgroup of some kind. And so the conjecture is that these 3 things, although they probably sound pretty different, in fact are pretty different, the conjecture is they're all equivalent. And so what I'm going to talk about today is some experimental work I've been doing attempting to disprove this conjecture, which I must admit I do not believe. And to rob my talk of all its narrative tension, I will just tell you now that I will fail miserably. So I'm going to tell you about a study I've been doing involving over 250,000 hyperbolic 3 manifolds, where I've been trying to compute these various properties, and so far I got nothing. Except enough to fill the next 45 minutes. How many are left? I'll get to that. I think I know the conjecture is definitely true for maybe half of them. I'm going the wrong direction. All right, so let me start just going through these 3 properties and trying to give you a little bit of feeling of what they are about. So the first one is the Heegard Floer homology. So this is something that associates to a closed 3 manifold Y a finite dimensional vector space over the field with 2 elements. It's essentially the same as the instanton Floer homology that Tom Rofka told us about last time. So as in that case, it's part of a 3+1 dimensional topological quantum field theory, meaning that associates to a manifold Y, it associates a vector space. And then if you have a cobordism between some manifold Y1, so you have this cobordism W, some 4 manifold, to some other 3 manifold Y2, then you get a map from this from the Heegard-Floer homology of Y1 to the Heegard-Floer homology of Y2. So it's not just a vector space, it's a vector space, sort of, a functor from the cobordism category. So these Floer homologies were introduced for three manifolds, really starting in the early part of this millennia. Maybe the first big result that was proved using them is this following statement of, it's proved by Kronheimer, Mrafka, Osvath, and Szabó in 2003 using the Seiberg-Witten variant of this theory. If you look at a knot in the three-sphere, one of the most basic topological operations is to do Dane surgery. So take the figure 8 knot. We take a neighborhood of this. Oops. And we take a neighborhood of this thing, which is a little solid torus. And then we remove that. So what's left is the exterior sitting in S3. And then here's the solid torus we had that I took out. And then the process of Dane surgery is you glue these pieces back together by identifying their boundary. And of course, if you do this by sort of the identity map, you get the three-sphere back. But if you take some more interesting gluing map that takes the curve here, which bounds a meridian disk, maybe to something that winds many times around the original knot, then you get some other closed three-manifold. And so you can ask what changes about your three-manifold when you do this operation. And so the theorem they proved is that if you take a non-trivial knot, such as this one, then no matter how you do Dane surgery on it, you never get RP3. So the unique way to get RP3 by Dane surgery on a knot is to take the unknot. We took the unknot and then glue in this solid torus. So this thing winds twice around that. That gives you RP3, sorry. And that's the only way to do it. So the tools of Floer homology have proven very successful at solving long-standing problems such as this one, which had proven resistant to the sort of Thurstonian tools of hyperbolic geometry that I personally am more familiar with. There's some sense in which it kind of captures orthogonal information. And the reason it is so useful in this context is exactly this functoriality with respect to cobordism. So if you have three different ways, three different Dane surgeries on the same knot, then in certain cases you get a long exact sequence involving the Heegard-Floer homologies of those three manifolds. And so that, unsurprisingly, gives you a powerful tool for studying Dane surgery. Now, the only thing that's really relevant for us today is this basic fact that the dimension of this vector space is always at least as big as the size of the first homology. Right? So for me, Y is always this rational homology three-sphere. So this is just some finite group. So even for the three-sphere, this Heegard-Floer homology, HF hat, is not trivial. It's just one-dimensional.
What do you mean by the size?
It's a finite group. Right? So Y is a rational homology sphere. So H lower 1 with rational coefficients is 0.
You mean coefficients Z2 and not Z?
No. Right? So here, right, I'm assuming that H1 of my three-manifold is 0, which implies that universal coefficients, that this is finite. So I really just mean the size of this group. And so when you have an equality here, when you have as little Heegard-Floer homology as possible, that's what's called being an L space. And the name comes from the basic example of such manifolds, namely anything that has a spherical geometry. So in particular, a lens space LPQ, its Heegaard-Floer homology has dimension exactly equal to P. And you can then think of these L spaces as kind of generalizations of lens spaces from the point of view of Heegaard-Floer homology. So now there are many examples of things which are not L spaces. So if you take a knot in the 3-sphere other than the unknot of the trefoil, for example, this figure 8 knot, and if you do one-on-end Dane surgery, so that means you do something which winds once around this way and n times sort of around the long way, then Kronheimer and Moravka proved that you always get a non-L space. And that's part of the same story that Tom was telling us about last week that goes through the theory of foliations and gauge theory and work of Gabay to hierarchies back all the way to Haken. So this is a giant result, but it's easy to exhibit using it many examples of non-L spaces. Other questions so far?
Are there L spaces that are not spherical?
Yes, many of them. So another example, which maybe would have been good to say, if you take an alternating knot, well, for example, the figure 8 knot, but I'll draw it again because I can. If you take the twofold branch cover over the 3-sphere with singular set this, that is something which, oh wait, that one's still spherical. But if you take an arbitrary alternating knot, more complicated than this one, and you take that twofold branch cover, it's always an L space. And those typically aren't spherical manifolds. It is for something like that. So that's what I wanted to say about Heegaard-Floer homology. Other questions? I mean, maybe just to say one sentence about its definition. It comes from looking at a Heegaard splitting of the 3 manifold. So viewing the 3 manifold as 2 handle bodies glued together along their boundary, which is the analog in the 3-dimensional context of like a group presentation. And it's some kind of basically Lagrangian Floer homology associated with certain configuration spaces built from that diagram, that data. So you take some description of your 3 manifold, you look at some configuration spaces, you take some symplectic, well, not quite symplectic, anyway, some Lagrangian Floer homology, and you get this thing. And as I said, there are variants that involve things where the generators of the chain group are representations to SU2. That's what Tom was talking about last week. There are variants involving Seiberg-Witten equations and so on. But for us, it's just a black box. Really, all you need to know is there are 2 kinds of things from the point of view of Heegaard-Floer homology. They're the L spaces and the non-L spaces. So the second thing the second of our 3 seemingly unrelated concepts is sort of purely algebraic. So a left order on a group G, is just a total order on its elements, which is invariant under left multiplication. So that whenever you have G is less than H, and you pick another element F from your group, you have to have F times G is less than F times H. So maybe the most basic example of this would just be to take the real numbers with the operation of addition and take your usual order on the real numbers. Now here we'll mostly be interested in countable groups. So maybe the integers under addition is a better example. And lots of big groups. For example, the free group turns out to have many, many left orders, as does the braid group. There are other groups that are not orderable, such as finite groups. See, the basic thing is that if you have an element in a group, which is left orderable, then either it's bigger than the identity, or it's equal to the identity, or it's less than the identity. And if it's bigger than the identity, then left invariance tells us that G inverse is smaller than the identity. And in this case, it would tell us that G inverse is bigger than the identity. In fact, you can think of it as sort of a partition of G into positive elements whose inverses are the negative elements, which is where positivity is closed under multiplication. So in particular, if you have an element of finite order, you get into trouble with this very quickly. Right? If your element G is greater than the identity, so is any positive power of it. That's, again, the left invariance. So if some positive power is also its inverse, you're in trouble. So finite groups are not left orderable. I guess this group has torsion, so it's not left orderable for the same reason. But it's also true that any finite index subgroup of SLNZ, many of which are torsion-free, none of those guys are left orderable. For countable groups, like the kind of thing I'm interested in today, being left orderable is equivalent to saying that you are a subgroup of the group of orientation-preserving homeomorphisms of the line. So you can think of it then, if you're seeing it for the first time and of a more geometric mind, this is perhaps the definition I should have given. To say you're left orderable just means you have a faithful action by your group on the line preserving orientation. So it turns out that those groups can be very, very complicated, including things like free groups and Bray groups and so on. So today I'm going to be interested in when the fundamental group of a three-manifold is left orderable. So just for notation, I'm going to call the three-manifold itself orderable if its fundamental group is left orderable. Are there questions? So some examples of non-orderable three-manifolds would include, for example, spherical manifolds, as they had finite fundamental groups. And something that has orderable fundamental group would be, for example, S2 cross S1. So to move on to our last of our characters in this play.
That's what it means to have non-minimal for homology to have the size bigger than the size of H1 in this case.
Yes, that's right.
So that's what you're saying.
Yes. So to go back, I'll recap my conjecture in a minute. But the first of the allegedly equivalent conditions, which was the Hegardt-Floer homology, was non-minimal. That was in reference to this.
There are examples that are not
That's right.
spherical.
That's right. So a taut foliation is a decomposition of my three-manifold into two-dimensional leaves. So locally, it just looks like a stack of planes. And I won't make any real smoothness assumptions on this. This is kind of a technical point at first sight, although 2 years ago we saw a very nice talk by Rachel Roberts where she explained how you can actually deal with foliations of three manifolds of kind of minimal smoothness. So this means that the leaves are C1 embedded, and the tangent planes to the leaves vary continuously. But you can just pretend it's smooth. I'm always going to insist my foliations are co-orientable, so they have a consistent normal direction. Since my manifold is orientable, that's equivalent to saying the leaves are orientable. So we have orientable leaves. If I don't add this third condition, this turns out to impose no restriction at all. So any closed three-manifold has a foliation, in fact, even a reasonably smooth foliation, which is co-orientable. So these are very, very common. But when you add this slight additional condition, that there is a loop which is transverse to the leaves, never tangent, transverse to the leaves, and it meets every leaf, that turns out to be something that greatly restricts the topology of the three-manifold. And so if you have all three of these things, we call it a taut foliation. So a basic example, if we have a three-manifold that fibers over the circle, so we have a surface bundle over the circle. If Chris was here, I was going to say we should pick his favorite pseudo-Anosov homeomorphism. Then I was worried are they all his favorite? So we have our foliation of this guy by the preimages of the points in our bundle. And so, okay, where's part C? Well, we just take a loop through this guy transverse like that. Now, this is not a typical example in that all of the leaves here are compact. So most of the taut foliations we'll encounter today, they're closer to something like this. If you take the three-dimensional torus, if you think about it as the quotient of R3 bod Z3, if you take a plane of irrational slope and all its parallel translates, that's preserved by the deck group and folds down to a foliation of your three-dimensional torus where every leaf is dense. And that's a much better example, but harder to describe. So as I said, every closed three-manifold has a foliation satisfying A and B. That actually, one way to prove this is to use the fact that the mapping class group is finitely generated by Dane twists, random aside. If you have a taut foliation, then the universal cover of your three-manifold has to either be R3 or S2 cross R. In particular, it's non-compact, which means that the fundamental group is infinite. So things like lens spaces, our simplest examples, they do not have these taut foliations. There are plenty of other hyperbolic three-manifolds, for example, which don't have taut foliations. The Weeks manifold, which is known to be the manifold closed hyperbolic three-manifold of least volume, it was proved by Roberts, Sharishian, and Stein that it has no taut foliations. So, other questions? All right, so further, I've got three things which seem unconnected to one another. Let me try now to connect them. So here back up are the three things we saw in the original conjecture. So we have that the Y here is a irreducible rational homology 3-sphere. Here we have that Y is not an L space, so Hegardt-Floer homology non-minimal. Over here we have that the fundamental group of Y is orderable. And over here we have the condition about taut foliations, that Y has a taut foliation. And so the original conjecture I had up is that these three things are equivalent. And just for notation, I should say that when I say something acts on something else, I'm always going to assume the action is non-trivial, although not necessarily faithful, and that the action is orientation preserving. So you might quibble that this implication is not clear. If you're orderable, you certainly act on R. And it turns out it's a theorem of Boyer, Wolfson, and Weiss that for three-manifold groups, you can promote non-trivial actions to faithful actions. See, we don't really have to, I'm never going to really worry about when things are faithful, consequently. So amongst these three things, there's only one theorem known. These are dotted things. These are supposed to indicate conjectures. And that's this result here. So in this form, it was proved by Osvath and Szabo. In the generality I'm talking about here, it uses recent work of Kazaz-Roberts and others, Jonathan Bowen. So this is the whole sort of gauge theory story that I alluded to earlier. The idea is if you have a taut foliation, you can perturb it to get a tight contact structure. So you have a foliation is an integrable plane field. So Ashberg-Thurston and then these guys in lesser degrees of smoothness showed you can always perturb that plane field to get a contact structure, so something that's maximally non-integrable, by moving it just a tiny bit. And it turns out you kind of do this in two ways, sort of twist positively and negatively. And that gives you, if you look at Y cross R, so that's a 4-manifold, it allows you to put a symplectic form on that 4-manifold, which has those two contact structures as kind of at the boundary. Now, if you know about things like Taub's non-vanishing theorem, that starts to give you some purchase into these 3+ one-dimensional TQFTs. You can show some certain things that are non-zero. And by the analogs of those kind of results in this particular context, so really this goes to have like Ashberg-Thurston, and then you can pluck this symplectic thing, and then this big results of Osvath and Szabo, and so on. You eventually go from this taut foliation and build some non-trivial class in Hegardt-Floer homology. So that's the one theorem we have. So there is something here. There's really no known results that directly connect these. But there are, in fact, other connections that make this somewhat more plausible, or maybe arguably more interesting than it would be otherwise. So in particular, let me start with this. So if you have a taut foliation, it turns out you don't necessarily get an action on R, but you do get an action on some kind of one-dimensional object. So I mentioned that if you have a taut foliation, and if you're in the case we are, where you're a rational homology sphere, then the universal cover, so we have our foliation F of our three-manifold Y. The universal cover of this is going to be the 3 sphere. Sorry, it's going to be R3. And it's going to, you look at the pullback of this foliation upstairs, and what tautness buys you. I mean, somehow, I like to think of tautness as saying somehow the transverse dynamics are interesting. It's not exactly true, but maybe it's morally true. The picture we're going to get up here is these guys are all planes. They're the universal covers of the leaves downstairs. So upstairs we have R3 foliated by planes. I mean, the simplest thing you can imagine is it's just a stack of planes. Right? This is what would happen in the case of the 3-manifold that fibers over the circle. Right? Because there you take the universal cover. It's like you take the universal cover of the surface, that's your plane, together with the universal cover of the circle. Right? So in particular, we can form something called the leaf space of the foliation by collapsing each of these leaves upstairs to a point. So in this case, what I would get is a line. And of course, the action of the fundamental group acts by deck transformations on its universal cover, permuting these leaves. That gives us an action here. And this picture is not the most complicated thing that can happen. In general, there's some kind of non-Hausdorff behavior that comes out.
Why?
Glad you asked, Ilya. So the picture you should think of maybe as this. So here's my universal cover, this open domain, which is homeomorphic to a ball. And maybe the leaves are things like just the intersections of this with planes. And so now if you go to the sort of missing point here, at this point, we have these 2 leaves which almost but do not quite touch each other. So if we collapse each of these leaves to a point, what we get is a non-Hausdorff one-manifold, like this. So the topology, I didn't say what the topology is, but the topology on this leaf space comes from transversals. So if you take a little transverse arc, that's supposed to project to give you a chart on your guy. So the leaf space, it turns out, is always a one-manifold if you allow your one-manifold not to be Hausdorff. And it turns out it's also always simply connected.
Some kind of dendrite, right?
It's some kind of dendrite. So if you sort of hit it with the Hausdorffification hammer and just insist it be Hausdorff, you get an R tree.
Right, okay.
So if you have a taut foliation, your fundamental group acts on an R tree. But it doesn't preserve any kind of transverse measure. Okay. So that's an action on a one-dimensional thing. There's a second one-dimensional action that you get from a taut foliation via something called Thurston's universal circle. This is a beautiful theorem of Candel that if you have a taut foliation like this, you can put a Riemannian metric on your 3-manifold so that each leaf is of your foliation, these 2-dimensional leaves, they're actually constant curvature -1 on the nose. So when you go to the universal cover, these are not just sort of, quasi-isometric or something to H2. They're actually copies of H2. Still have the factory stickers on them. So in particular, they have circles at infinity. And Thurston came up with a way that allows you to sort of identify these circles together. It's much more complicated in a picture like this. And the universal circle is it's kind of an inverse limit. You somehow get like a map from this circle to this circle, and this circle to this circle. And of course, my whole picture is much too simple, right? This is really some, if it does this at all, this is some horribly fractally branching thing. But anyway, there's an inverse limit called Thurston's universal circle, and so you get an action of your fundamental group on that.
So on this tree,
Yep.
I understand that you probably cannot solve for an asymmetric action, but I mean, is there maybe some kind of an affine structure? You know.
I mean, for certain foliations there are, and for certain others there are not. So, so Thurston never published his proof of the existence of the universal circle. There's a Danny Caligari and I wrote down a somewhat different proof of that fact. All right, so we do have some ways to go from having a taut foliation to actions on one-dimensional things. They're not the line, but and more elementary, if you have an action on the line, well, certainly that gives you one of these. The real line is the only reasonable, simply connected one manifold. And you also get an action here just by saying, well, I have an action on a line, so pick a point on the circle, identify the line with its complement, act by whatever you're doing here, and just fix this point. Okay. So now we have at least a little more connections between these things. And so now you can start to imagine maybe if some of these arrows I have here are invertible, or at least a lot of the time, you can start to build a bridge going from here over here.
So, I mean, you said told us in the beginning that you don't believe that.
I don't.
So, which of the dotted arrows do you think might be false?
This one, this one.
Wait a second. No. I mean, of the dotted arrows.
Oh, dotted arrows. Both of these, this one,
Okay.
I don't believe this one. This one's definitely not invertible. This one's definitely not invertible.
Okay.
But that's what I say, but I have nothing. Okay, I got nothing. I mean, this is actually a project I've been working on for over 10 years, or at least maybe exactly 10 years. When the results of Kronheimer, Moravka, Oswald, and Szabó came out with these sort of effective,
But
yes?
basically, you think that the remaining dotted arrows there, none of them are.
Well, that would be my guess, but for the simple reason I don't see any way to construct. So, I mean, here there is some way you could try to go backwards. This is like saying you have an action on a simplicial tree is dual to an incompressible surface. And people have tried hard, people far smarter than I, have tried to avert this arrow without any success. And in fact, my motivation for starting this project 10 years ago is I wanted to prove that there was no arrow here. And I wanted to use this newfound, the fact that you have this implication here to find a three-manifold which acted on, say, the line, but via computing its Floer homology and using this implication here, I could show that it didn't have a taut foliation. That was my plan, and now I tell you the story of failure.
So can you reverse that arrow?
Which one?
From the upper corner down diagonal.
This one?
Yeah, is it reversible?
No.
That's no, not to be.
Oh, no, not to be. No. I'm not sure, actually.
Might be true, actually.
Conceivably.
But like, so it's like a tree, right? Or it seems like an tree.
Yeah, I mean, you should think about you're acting on an R tree, and you want to turn that into an action on R. You kind of have to fold everything, sort of comb it and fold it up into a line. And it doesn't seem particularly likely you can do that. But. So, okay, so despite my going on about how I don't believe the conjecture, there's a lot of evidence for it. So one of the best results is last year, Hanselman, Rasmussen, Watson, combined with work of Boyer and Clay, proved that it's true for all graph manifolds. So a graph manifold is just anything you get by taking Seifert fibered spaces and gluing them along tori. So in particular, if you take like a pair of pants cross a circle, take a bunch of copies of that, glue some of their tori together, take some solid tori, glue those into the remaining boundary components you have. such things can be quite complicated, and they proved using sort of advances in computation of Hegardt-Floer homology, they were actually able to show that all these guys are, that the conjecture holds for them. Here's another sort of sample result. I'm dispirited enough now I'm trying to prove the conjecture. If you have a knot in S3 and there's some condition on its Alexander polynomial, it has a simple root on the unit circle, there's some technical condition. Anyway, something that happens a lot, then if you look at sufficiently large Dane surgeries, things that are close to the longitude, then the conjecture holds for them. This combines my results with Mark Kohler with works of Roberts. And there's lots of other work involving branch covers, some of which I alluded to, so on. So it's actually known to be true a surprising portion of the time. OK, so what have I been doing? So I've been looking at about 250,000 hyperbolic rational homology spheres. So in particular, they're not going to be covered by this result here. And for technical reasons, I chose them to be twofold branch covers over non-alternating links in the 3-sphere. This is just some plot which is supposed to indicate a sense of scale. It's not useful, though, unless I tell you that if we look at, say, the figure 8 knot, and you look at the complement of the figure 8 knot, the hyperbolic volume of this thing, which is the smallest of any knot in the 3-sphere, is like 2.02988 something something. And so these guys, they're not super complicated. Their average volume is 7. So maybe you should think of them as like a 20 crossing knot or something like this. And then from the hyperbolic geometry point of view, looking at their shortest geodesic, the length of the systole, the injectivity radius is a natural thing, and this is some plot of that. So here are my results. So I was able to determine exactly which of these guys are L spaces and which are not. So it turns out some 73% of them are L spaces, and 27% of them are not. For the orderability, I can show that at least 44% of them have non-orderable fundamental group. So that's about 60% of the ones inside here. So anything in this box, the conjecture is true for. Amongst the non-L spaces, there's a small portion of them, it's about 10% of the total, where I can show the group does have a left order. And for something like almost 90% of them, I can show that these non-L spaces have a taut foliation. So then the guys in here, less than 3%, the conjecture also must hold for those. So are there questions about those results?
So, I mean, I understand this is not a complete story, but so there's a big difference then. The orderability seems hard to prove. It's hard to prove that something is orderable?
Yes, it is. So the thing that makes this tricky is that, oddly enough, it's the Floer homology that's the easiest of these things to compute. So you do know that determining whether or not something is an L space, that is decidable. There is an algorithm that would compute it. It's probably, time is like factorial in the size of the input, which is bad, but it's not like horrendous. To the best of my knowledge, it's unknown whether you can decide if a 3-manifold is orderable. The general question of does a given finitely presented group, is it left orderable? That's undecidable. But I mean, any question about that. Any question of that kind is undecidable. But 3-manifold groups are extremely special. Hyperbolic 3-manifold groups even more special. So it's perfectly plausible there is some way to determine that, but it's not known. So I'm using various kinds of tricks. I will get to them. And then for the taut foliation, you can almost, literature's a little fuzzy, actually. You can determine things that are close to being a taut foliation, but maybe not exactly. It should be doable in the sense that you should be able to prove there exists an algorithm and describe it, but never implement it. Yes?
It's a silly question. In this render, that's all what you know, right?
This is just what I know, right? So at least 44% of them have non-orderable fundamental groups.
The rest of them might be also non-orderable.
That's right. Well, except for these guys.
We just don't know, right?
Right, except for the ones in the orderable box. Right, these guys are definitely not non-orderable. But yeah, the rest of them, everything out here could go either way. I have no information.
Another silly question. How did you pick those 265,000?
Well, they were the sort of the ones I had lying around. So they're twofold branch covers of links with at most 15 crossings.
So it's not like you pick all like triangulations of manifolds and count them. It's
No, but I would if I could. So enumerating manifolds by triangulations is very difficult. You don't get anything as big as this. Those sort of too small. But yeah, as you think about this is basically, so the Jorgensen-Thurston theory tells you that if you bound the volume of your hyperbolic manifold from above and you bound the injectivity radius from below, that's a finite list of manifolds. So this is something like I bound the volume from above by about 13. Well, I'm not really bounding injectivity radius below by much, but OK.
So
Anyway, it's just some large collection of manifolds that are small enough I can still try to compute this stuff.
adorability, I mean, it's kind of a delicate property with respect to finite covers, right? I mean,
Oh, yes. So by the results of E and Agol, all of these groups are virtually orderable.
right, and that's not at all good enough.
And it's also true that they all virtually have taut foliations. If you allow yourself to pass the finite covers, all this stuff changes. And there's some very interesting concepts. If you believe this conjecture, that then gives you that the Floer homology has to behave in certain ways under finite covers. And in certain cases, Lidman and Menelescu have actually been able to prove that certain of these things behave that way. So yeah, it's not invariant under finite covers. Were there more questions about this? So for the last little bit, I just wanted to sketch something about how I computed these things, which I just spent time saying can't really do deterministically. So I found almost 64,000 taut foliations. And I did it by using a sort of combinatorial certificate. So involved looking at triangulations of your three manifolds. So these are not like simplicial complexes. These are just CW complexes where your cells are tetrahedra and you're gluing faces together by affine maps. So in particular, the ones I was working with had only a single vertex. And then I had this additional structure to them, something I call the laminar orientation. So it's just an orientation of the edges which satisfy three conditions, which the only thing that's really important is that they're combinatorial to check. So you're supposed to have an orientation so that every tetrahedra looks like this picture. So in particular, there's kind of a source vertex, and the arrows in our orientation all kind of go up from there up to the sink vertex. So that's what this is. Well, I guess this condition here is just that there's no triangle where you go around it in a consistent way. That turns out to say that every tetrahedra looks like this. And then there's some, maybe I won't belabor these things, or, well, by which of course I mean I won't explain these things. Just these are combinatorial conditions. You look at your edge labels, you compute some stuff, you check patterns around edges and things, and then you either conclude it is a laminar orientation or it's not. And my main result then in this direction is that if you have a triangulation which has a laminar orientation, then it turns out to have a taut foliation. So then for those 63,977 manifolds, I went searching for triangulations, and for each one I looked, is there an orientation satisfying my laundry list of conditions? If so, yay, save triangulation, put it on the list, and move on. And the technique here, to say something very briefly, really relies on the work of Tao Li constructing taut foliations. So inside each tetrahedron, you look at this thing here. This is called a branched surface. So it's like a train track, but one dimension up. So it has some kind of additional singularities here. But it turns out that on each triangle, you have these orientations of the edges, and you draw this little picture like this. Then every tetrahedron looks the same, so then you fill in such a guy. The theory of these branch surfaces, I mean, they really go back to normal surface theory and Hawkins' original work in describing normal surfaces. But the point is there are combinatorial conditions developed by Tao Li, which in favorable circumstances will tell you that you can find a taut foliation, which is basically carried by this branch surface, analogous to how a train track on a surface would carry a curve. And so there's these conditions about no sink disks and so on, and these are exactly set up so that they check his boxes and tell you you have a foliation. And then about the other parts, in fact, the reason I looked at these twofold branch covers is Lipschitz, Osloff, and Thurston have developed this whole very beautiful theory of bordered Hegardt-Floer homology. So, I mean, you have this 3 plus 1 dimensional TQFT, so you're assigning vector spaces to 3 manifolds and then basically numbers to 4 manifolds. And so if you look at 2 manifolds, there is something that gets associated to the end of these guys. But it's not something like a vector space. It's some kind of A infinity algebra over some A infinity ring. And you can use that, at least in theory, to effectively compute Hegardt-Floer homology. And the one case where someone's actually worked this all out and then gone the next step of implementing it is in the case where the 3 manifold is a branch cover, twofold branch cover over a link in the 3 sphere. So in particular, Jean implemented the strategy of Lipschitz, Osloff, Thurston, and so you can actually just basically input these things, and it grinds out and tells you, okay, this thing has HF hat of dimension 19. For showing a group is not orderable, I mean, for me, they're showing it's orderable or not orderable. They're independent. I just run them, and eventually maybe one of them answers, or maybe they don't. For non-ordering, you just look at some finite part of your group. So you look at you fix some generators, you look at the Cayley graph, you look at a ball in there, maybe has, I don't know, 30,000 elements, something like this. And in that ball, you try to decide, is there a way to declare some of them positive and all their inverses negative, which is compatible with the left order axiom. Of course, now sometimes you multiply guys together and they leave the ball, so we just ignore those multiplications. So sometimes you succeed. You got this pile, 15,000 elements, so your positive words. And sometimes you fail. And if you fail, well, you can't order the whole group. You can't even order this ball. And
That's really what you do?
That's really what I do. Now, it is true that if you can order every ball,
I think he uses a computer.
I use a computer.
Yeah, I understand, but I mean, I thought it would be something smarter, but okay.
So if you can order every ball, then it, by some kind of inverse limit or compactness, however you like to say it, you can order the whole group. But you never figure this out. You just keep ordering bigger and bigger balls. And to be able to implement this, to check that it really is in order, I need to be able to solve the word problem. And the way I solve the word problem is by using matrix multiplication. So these are really subgroups of PSL2C. You have some numerical approximations of their entries. And so then you just compute with these guys. And that turns out to be, I used to use like short Lex automatic structures. That was great, but it was too time consuming. To show something's orderable, I basically have 2 tricks, only one of which I listed here. If you can find a representation to the Lie group PSL2R tilde, the universal cover of the Lie group PSL2R, that acts on the circle, that acts on the line basically because the downstairs group PSL2R acts on the circle. So if you can find a representation to this thing, there's your action on R. And that's basically saying you find you find a representation to PSL2R, of which there were many. There were about 8 per manifold. And then there's an obstruction to being able to lift that to an action on R. Obstruction is the Euler class, analog of the first Chern class. So you calculate whether that vanishes. And so I got 7,382 of them have orderable fundamental group from this trick. But this trick has limits. It's the trick that everyone uses to prove many of the results I alluded to earlier, but it only works so well. All right, well, the bell has rung, and I'm out of slides, so let me stop there.
All right. Are there any questions for Nathan?
So you must have some strong intuition that tells you that it's false if you've been working on it for 10 years.
Well, yeah, I guess, I think it's the sunk cost fallacy. It's like, providing a bunch of evidence in favor of conjecture, it's like, yeah, right? But if I could disprove it, that would be like, work. I'd get something out of it. So it's like I'm chasing. No, but I mean, I have this work with Mark Kohler. There really are clearly, I think the conjecture is false, but that doesn't mean that something close to it is not true. So I could imagine that you start weakening, instead of saying left orderable, you just say acts on a simply connected one manifold. Something like that. Maybe then, there's so many things and patterns that people have found that are parallel in the different things. There's clearly something going on. I don't think it's going to be quite this simple, but clearly there is something going on. So it's probably kind of true. Certainly, I can't disprove it. Let's put it that way.
Yes.
So yeah, I guess I'm following this question. I mean, this action on the tree, right? You can get it from a foliation.
Yep.
But I mean, can you make it something similar to like an isometric action?
No.
There is no way to. There is no kind of additional structure, right? Transfer.
Well, I mean,
or something.
no. So, I mean, of course, if you assume your foliation downstairs has some kind of transverse structure, like a transverse measure or a transverse projective structure or something like this, then that will lift to this object. But there's no reason to think that they will have them. Typically the dynamics here, there'll be lots of things like points that are fixed and everything's contracting them towards them. They don't look very isometric generically. But I think, in fact, the results I have indicate that there must be a ton of taut foliations with transverse projective structures. I mean, the fact that this doesn't work to find a counterexample, I think, suggests this.